Ladies and gentlemen, please welcome to the stage representatives from Idaho National Laboratory and the U.S. Department of Energy.
Well, good afternoon, everybody. That would be a really fun way to announce that I have a new job. Better than a LinkedIn announcement, I guess. So I'm Rian. I'm the Deputy Assistant Secretary for Nuclear Reactors in the Office of Nuclear Energy. And for those of you that are paying attention, nuclear is having a moment. It's a really exciting time. And the President on May 23rd announced 4 executive orders that do a lot and say a lot, and more importantly, are intended to reinvigorate the nuclear industry in the United States. And they set a goal of increasing nuclear energy capacity in the United States up to 400 gigawatts by 2050. And there's an understanding in this community, in our community, that part of that energy generation is going to be needed to accelerate AI. So nuclear energy for AI. And actually in one of the executive orders, it directs the Secretary of Energy, who's going to be speaking today in general about AI, to look at DOE sites for siting both nuclear reactors and AI infrastructure. So nuclear energy for AI, but I'm equally excited about AI for nuclear energy and taking advantage of AI to accelerate nuclear energy deployment. In the Office of Nuclear Energy, we are directly and actually indirectly investing in frontier AI applications to do things like automated design and licensing reviews for nuclear reactors, automation for microreactors, a whole lot of things. That work is being executed at Idaho National Laboratory, and I'm so honored to be sharing the stage with the real brains in the speakers. So I'm going to turn it over to Chris Ritter to walk you through. But thank you again.
Thank you, Rian. So it is a very exciting time to be at Idaho National Laboratory. As Rian mentioned, we are at this period where at pretty much every angle is looking for more nuclear. There's a liftoff report, which was from last year, which called for 200 gigawatts of new nuclear energy. As you heard from Rian, we're now looking at 4 times the nuclear energy deployment that we currently have in the US. 8 labs put together a report on AI applications for energy. And Chapter 1 looked at nuclear energy and the things that we could do to accelerate nuclear deployment in the US. And then, of course, Secretary Wright, in his latest memo, we saw a look for abundant nuclear energy and rapid deployment. Nuclear energy is mentioned many times in his memo. There's been a lot of push, which, of course, you will hear from Secretary Wright in about 27 minutes on the South Stage. So that'll be a great talk to hear. So if we look at the competitive standpoint, and by the way, this slide, we have to go through lab approvals, is now dated because DeepSeek unveiled 0528 model last week, right, which is now near parity of our latest frontier models, comparing most of the benchmarks. Also, we saw the original DeepSeek R1 model had already made significant improvements from a reinforcement learning perspective, using that instead of a human labeled data approach. DeepSeek v3 was already near kind of our traditional LLM models. And then on an energy standpoint, and the thing that maybe should scare us the most as a country is our ability to deploy energy is not fast enough. On a nuclear perspective, this kind of tells the story really well. You know, China's at about 32 gigawatts of new nuclear currently in the pipeline. The US has 0. Now there's a star there. We have 4 permits approved, and we are working to get more nuclear. But when you think about the power energy demands, we need to invest more in nuclear energy as a nation, and we need to get a lot faster. So we need to start thinking about what are the changes that we need to make nuclear happen in a much quicker way. So there is some good news, right? So with bad news, we always have some good news. The hyperscalers, who are all here, are investing in nuclear energy. In fact, there are announcements. Again, these slides, we do them a week early, and then things change. Amazon is investing in X Energy with a $500 million investment. Microsoft announced recently their investment in 3 Mile Island to really rapidly deploy data centers using those units. And then Google is investing in a new startup called Kairos as well. And Meta just recently announced, I think yesterday, a partnership with Constellation Energy to deploy nuclear in the Illinois area. And they're looking for up to 4 gigawatts of new nuclear capacity. So we are seeing the hyperscalers engage in a big way, and there's more to come when it comes to hyperscaler involvement in the nuclear energy space. So if we look at So we talked a little bit about the needs for nuclear to power AI. There are also a lot of applications where AI can really help nuclear. And we'll talk about three primary ones today. The first is accelerating deployment and licensing. So if you think about the nuclear design process, right, it can take about a decade to go through. What can we do to accelerate that approach, in some parts of the process by up to 50%? What can we do to accelerate new fuels and materials in our laboratories? And then what are ways that we can autonomously operate, at least semi-autonomously operate some of these reactors that we're deploying, especially the microreactor ones, right, directly alongside a data center. And then of course, how can we demonstrate that these things actually work and take them out of the labs and directly into the nuclear industry itself? So if you look at the first application on the left, you will see a video of just like a text prompt you put in. It's going to be like the control room is 10 feet by 20 feet. The reactor hall should be 40 by 50 feet, so on and so forth. You get the idea. And then it's taking that text, right, and automatically converting it into what's called an industry foundations classes file. So these are CAD files that are directly used for building applications. We have newer tools that will optimize the layout too automatically and build up that geometry that's needed to design the plant. So that's one aspect. And then the other aspect, which I think I'm gonna have to manually play, the video on the right, you can take those CAD geometries and you can automatically then use, this is a deterministic program, but it will take that geometry, automatically mesh it into formats that then can be used for analysis. So this is a seismic analysis. So it's gonna import it. This is not fully autonomous. You'll see the human come here and click a couple buttons to remove the elevator shaft, but it's near autonomous. So it can reduce the workload of going through a CAD design process and then a meshing process from what would usually take months down to just a few days, right, for someone to go back and forth. And this is very early tier level technology that's at a low level of maturity, right? We have to accelerate it and make it work for more geometry. If you try to put in like a dome geometry, it doesn't work yet, right? There are things we need to do, but you can kind of see the idea of some of the early technology demonstrations of the work that we're accelerating. The second application, maybe one of the least obvious in the nuclear space, I think the clicker will do it this way, is autonomous laboratories. So Oak Ridge, who I think is in the audience, is also doing a lot of work on autonomous laboratories in the science space. So all the national laboratories as a whole are looking at ways that we can do more AI acceleration in our own labs. So on the nuclear side, we have made a huge investment in robotics. We do not work for Boston Dynamics, if you were here to hear that joke, but we are investing in tools like that and technologies like that inside our labs. So there's kind of two aspects to this. One, robotics to allow those labs to operate near 24/7, and also what we kind of call virtual irradiation, which is basically taking things that we typically would have to physically test and doing it all computationally. And that's evolution of things that we've been investing in for a long time. But the current state of the art, there's a lot of copy pasting that goes on between different models. Linking those workflows together would have huge returns, and of course, getting to more 24/7 operation of the labs, we're really excited about. And then the third use case, where we actually have a couple videos to share, is autonomous operation. So we've been looking at this for years, starting in 2020, of what can we do to get to more autonomy when it comes to operating a nuclear reactor. The first demo we did was an autonomously controlled non-nuclear microreactor. So what does that mean? It's a heat pipe in a facility where we had AI actually controlling that facility. And then the second application was a real digital twin of an actual nuclear reactor, so streaming that reactor through the cloud. We'll share those two videos now, and then we'll talk a little bit about where this technology is going at the moment with partnership. So the first is our magnet digital twin demo. So this demo used the magnet facility. You can see there in real time, it's plotting the power curves. And then those warnings that come up are when the autonomous reactor made a change. So it's forecasting the power levels 10 minutes out, and then using that forecast to control based on the future state of that facility. When we proposed this project, some people thought this would be impossible to do. So of course the labs like to do things that people say will be impossible. As far as the error rate, we got one shot to do this. So there was a candidate facility that was nearby that it was kind of on a table, had different thermal properties. We got to do this one time on this actual magnet facility for 1.5 hours. If it succeeded, it did. If it failed, it failed. With the exception of the operator clicking the wrong button, it was able to forecast within a 0.3% error rate. of what that reactor state would be. So really cool to see those kind of first demonstrations. And then 2 years later, NNSA funded a demonstration to do this for a real nuclear reactor. Now, we didn't do control. We'll talk a little bit about where we're headed with that. But we were able to, this is the AGN-201. So these are 5 watts of power. So think about a light bulb, right? These are very low power, but they're not small reactors, right? They're still a widthwise. And anyways, the AGN-201, these were built in the 60s. They're older technology, so that brings in different challenges that we had to resolve. So one, when you're talking about reactor technology that is from the 60s, you don't have digital controls, you don't have digital data acquisition, and you're dealing with a much older facility. So we first had to kind of go in and digitize the control system for the reactor to stream that data directly to the DAC. We partnered with Microsoft to use their Azure environment to stream the data to that cloud, and then we had multiple models running on it in real time. We had both a surrogate physics model, which was using first principles physics, and then we had a data-driven model that was using data in real time and time series from the reactor. And then we ran that model through a set of red team, blue team tests. So we took a group of students who inserted different things in the reactor at different points in time, and that red team was unknown to the blue team with what they were doing. And so basically the way we structured this, the red team had to present kind of their results to the blue team and back and forth within a 30-minute period. So there's no way to cheat, there's no way to run a big HPC run, right? You're compiling all your AI forecasts and then using that to forecast out where you're gonna be. And it turns out that approach with having multiple models worked out really, really well to detect how that reactor would operate. That technology was successful enough that we are now partnering with real industry partners to bring that technology closer to market. So Westinghouse Nuclear is working with us on a project also funded by NNSA to take that autonomy technology on the non-proliferation side and bring it to real commercial products. We also are working internally on more autonomy applications using our laboratory developed reactors to get closer and closer to near full autonomy. And so the last thing I'll really leave you with, and we'll open up for like 1 or 2 questions before we walk you all over to Secretary Wright, is the idea that we build these tools in the lab setting. Maybe, there we go. The worst thing that we could see happen in a lab setting would be that it stays in the lab setting, right, and doesn't get out to market. So what we're looking to do over time is we've already released as the Department of Energy, right, an RFI looking for building data centers at national laboratory sites. So that's a great opportunity, right, to pair these data centers with nuclear reactors in some cases to kind of see how the two would work and use AI to accelerate both the design of that reactor and then autonomously operate that reactor in conjunction. So you could imagine a future state where perhaps you deploy 4 modules of an SMR, 3 are always being used to operate that facility, and 1 can be doing refueling. If you remember, nuclear capacities rates are pretty high, right? 92% on average. And so you can kind of do this 3-on, 1-off approach to do that control. And then of course, do automatic, if you need to do refueling on more than 1 reactor at once, right? You can automatically tell the data center ahead of time to give time to spin down if it's a training workload that it's running, or if it's inference, right? Move it to a different region in time. So we're really excited about the potential to demonstrate this technology at scale in partnership with industry. And I think this is the most exciting thing happening with nuclear, where we're seeing this really close partnership when it comes to the hyperscalers, the nuclear vendors, and the national laboratory community at large. I'm going to leave it at 15 minutes. If there are any questions, we have time for 1 or 2 questions, and then we are going to walk you all over to Secretary Wright on that stage. So are there any questions from the audience? There's a mic right there. Otherwise, we'll start with that gentleman, Rob King, right there. I'm sure he has a question. What'd you say?
I said I have direct access to you. I can ask you anytime.
That is definitely true.
That's how you project.
So any questions from the audience?
Just on the SMR thing, are you expecting 4 SMRs to be standard for a data center, or is that just a number?
So standards for a data center, you mean, are we expecting that every data center to use an SMR? Is that what you're asking, or?
On a DUI, on a government site.
So I think you'll see a mixed use of power sources, right? So nuclear is great when you need a high capacity factor and you need great baseload power. So think about a training workload, right? Or definitely inference, where you don't want that workload to go down for a period of time. Nuclear is a great solution. But there are also energy sources like fossil and renewables that might be used in other cases, right? So I don't think, we are the laboratory inside the Office of Nuclear Energy, so we're doing a lot of work with nuclear, but we're seeing geothermal, for example, water, and fossil sources also taking a part of this play. And I think it's important that we invest in multiple energy sources when it comes to meeting the energy needs, right? Eric Schmidt, right, has said we need, 29 gigawatts of new power by 2027, 67 more by the end of the decade. And so to meet those needs, we're going to need an all-of-the-above approach, but nuclear is a key part of that answer. So any other questions from the audience? All right. So I promised we would end early, so we're going to walk you guys over to the south stage to meet Secretary Wright.